Problem 4.2-2. The problem statement reads, the radial dimension of a shaft is defined by the equation r is equal to 0.01 times the natural exponential function raised to the x in units of meters. The shaft is free at x equals 0 and fixed at x equals 0.7 meters. If a torque of 110 Newton meters is applied, determine the angle of twist at the free end relative to the fixed end. G is equal to 18 gigapascals, where G is our shear modulus. Here is our tapered shaft. The torque is applied on the free end. Here is the radius r, which is defined by the function above. Let's begin the problem. This is the form of the equation that we will be using to calculate the angle of twist. It is the integral from 0 to L of the internal torque T times dx divided by J, our polar moment of inertia, as a function of x, and also divided by G, our shear modulus. J will be a function of x because J is a function of the radius, and the radius is changing relative to x. T and G will be constants. I have expanded the equation for the angle of twist as shown. The limits of integration will be from 0 to 0.7 meters. T is constant throughout the member. It is 110 Newton meters. The polar moment of inertia is equal to pi over 2 times the radius to the fourth power, and the radius is written as a function of x shown above. The shear modulus is 18 times 10 to the 9th newtons per meter squared. I have simplified this expression now to make the integration a little bit easier on myself. To integrate, we divide this constant by a -4, and we are left with a new constant in this expression. We will evaluate it from 0 to 0.7, and we get a value of 0.0913 radians. It's positive. That means the angle of twist is in the direction of the applied torque. And we're done.